Welcome to the ePathshala lecture series in computer science. We are discussing about the computer architecture course. This module is about virtual memory. So, the objectives of this module are to discuss about the concept of virtual memory and look at the various implementations of virtual memory. So, first of all, the question of why virtual memory. So far what we have assumed is, we have assumed that whatever programs we write, the programs need to be available in main memory and they get executed from there. We have already looked at the concept of hierarchical memory system, and we have looked at how the cache can improve the performance of the memory by hiding the latency associated with your main memory access. But now we have to look at the main memory now, and we restrict our programs to be the size of the main memory, because we assume that the entire program has to be available in main memory for execution. Now that is not so. We do not have to restrict our program size to the size of the main memory. So what alternatives do we have like this to this? So just like how we discussed in the case of the cache, where we looked at the locality of reference principle and said that whatever portions that are needed by the processor or demanded by the processor, it is enough if we have those portions available in cache. Now we are extending the same concept here. So we do not have to assume that the entire program has to be available in main memory for execution. Only the portions that are actually required by the processor then and there on demand, it is enough if they be brought to main memory for execution. So the entire program can be available in secondary storage. So that is the concept of virtual memory. So the portions that are shifted from secondary storage to main storage, you can look at portions being of fixed sizes or pages, or they can be of variable sizes or segments. Now this permits a program's memory to be physically non-contiguous also, so that it can be allocated from wherever available. If you look at a program consisting of a number of pages or number of segments, you do not have to have them allocated in contiguous memories in your locations in your physical memory. One page can be located somewhere, another page on demand when it is brought in, it can be brought to some other place. So all these are advantages. So basically we try to overcome the main memory size limitation. This also allows you to do sharing of main memory among processes, because you can have multiple processes having their programs in main memory, and this is possible because you are only looking at the modules that are actually required by the processor for various processes being available in main memory. So there is a sharing of main memory among the various processes. So the virtual memory model basically does decoupling of addresses used by the program, which from now on we will call as virtual addresses or logical addresses, and the actual physical addresses, the memory addresses. And this also helps in physical memory allocation by way of either paging or segmentation. So as I just mentioned, pages are where you look at the portions being of fixed sizes, called pages. Segments is when you look at the program being of variable sizes, called segments. And this also helps in process relocation. So when you have a page located in some place, and then when the process is going idle for some reason, and then it is again taken up for execution, there is nothing wrong in loading its page in some other place. It is possible to relocate your pages, and pages are brought into memory only on demand. So the whole concept is, you do not have to locate the entire program in main memory for execution. Only the portion that is currently requested by the processor, either as a page or as a segment, it is enough if that is available in main memory for execution. The rest of it, the entire program, it is available if it's enough if it is available in your secondary storage, and only on demand the page or segment is being brought into main memory. So if you look at the definition of virtual memory as such, it is the conceptual separation of the user's logical memory from the physical memory in order to have a large virtual memory on a small physical memory. And this obviously gives us an illusion of an infinite storage, though it is not an infinite storage, it is just limited to the size of the virtual address. So this is a pictorial representation of the concept of virtual memory that you have. Say for example, you have the disk consists of a number of pages, or the disk consists of a number of segments, whichever portions you look at. You have a physical memory where these pages are being loaded, and you have a memory map, the virtual memory, where from the virtual memory you get the virtual address. So, those virtual addresses, by doing the memory mapping process that has been indicated here, the virtual addresses will be translated to physical addresses, and that will give you the identification or location of a page frame in your physical memory. And if it is not available in physical memory, the memory map, when you do the translation process, you find out that it is not available in physical memory and it is available only in the disk, that is a secondary storage. From there it is being brought to your physical memory for the processor to execute. So, this is the concept of virtual memory. So, this again gives you a pictorial representation again. So, you can see that you have 4 different pages with different addresses. Out of that, 3 pages are already available in physical memory. The 4th page D is not available in physical memory, it is available in the disk storage. So, when you translate the virtual address, when you do a virtual to physical address translation, you find out that the 3 of the mentioned pages A, B and C are available in physical memory. So, you will be able to access them. The 4th page D is actually not available in physical memory, it is available in secondary storage. In case if there is a reference to one of the locations in virtual page D, then that page D will be brought into your one of the pages of your main memory. So, it becomes a physical page frame, and from there it is passed on to the processor. So, basically what we understand from here is, we are not looking at just physical addresses, what we have been doing so far. You have a virtual address or the logical address, which basically tells you which is the page number. So, when you have a program, the program, depending upon the size of the program, it gets divided into a number of pages. So, you talk about page number 1 of your program, page number 2 of your program, so on and so forth, and the pages are of fixed size, say typically a few kilobytes in size, say 4 kilobytes or 8 kilobytes of size. So, you talk about a location within that 4K page or within that 8K page. So, when you talk about a logical or the virtual address, you give the page number. So, this is the 5th page of my program, 5th page, and this is the offset within the page. Within the 5th page, I am looking at one of the 4K locations. So, that is the offset. So, that is the logical or the virtual address, which gives you the page number and gives you the offset within the page. Now, this logical or virtual address will have to be converted to the physical address for you to find out whether it is actually present in physical memory or not. So, unless you do the translation or conversion, you will not know whether it is available in physical memory. So, we have to convert it to physical address. This physical address conversion gives us the page frame address in physical memory. Now, this is carried out by what is called the memory management unit. Now, this is an example which we have. So, the size of the frames or pages is defined by the hardware. A physical address is determined by, so you have your page number which gives you an index into a table, and if with the offset information, the index will map you on to a particular entry in your page table. So, the base address of the page table is known, the page number will help you index into the page table. So, you get the physical page frame address there. To that you add the offset, you will get the actual physical address. So, we look at the translation happening here. So, virtual address, if you look at the virtual address, it has a page number and it has an offset, and the page table that has been shown. So, the page table contains information about all the pages of that particular process. So, you might have multiple page tables for each process. So, the page table has multiple entries. The number of entries that a page table has will depend upon the page number. Suppose if you have 10 bits representing your page number, then obviously you can have 2 power 10 different pages. So, the page table will have 2 power 10 entries. Now, the base of the page table is available in what is called a page table base register. So, the page table is after all loaded in physical memory. So, where the page table, that particular page table is loaded, that base address is loaded into your page table base register. So, by adding the page number into your page table base register, you will be able to index into the actual page table. So, the base address is given to you by means of the page table base register. each entry size is known to you, the page table entry is known to you. So, the base address plus the page number into the size of the page table entry will help you index into a particular entry for that particular page. Say for example, if you are looking at page number 5, then you are supposed to index into the 5th entry into your page table. So, that process is done, and once you get into the page table entry, the page table entry will give you the physical address, page frame address, if that page is available in memory. If it is not available in memory, then it will tell you where it is available in the secondary storage, where a page fault will occur, and that page will get transferred on demand from your secondary storage to main storage. So, once it is available in physical memory, the page frame address is known. So, the base address is now known. The offset, when you add the offset, you will get the exact address and you access the data. So, this is an example of the page table entry. So, the page table entry has a number of features there. The first bit, M bit, indicates that's a modified bit. It indicates whether the page has been written into or it is still clean. It is similar to the dirty bit that we discussed with respect to our cache memories. So, it tells you whether the page is modified or it still remains clean. The R bit indicates whether the page has been referenced. This is basically useful for your replacement policies like LRU. Then you have a valid bit which tells you whether this entry itself is valid or not. Only if it is a valid entry you can consider it to find out the physical page frame address. And then you have the protection bits. Protection bits which actually tell you about the access right of that particular page. What type of access can you have on that page, whether it is read and write access or a read only access or an execute only access. What are the access information that you have on this particular page. And then of course, you have the page frame number which gives you the physical address of the page that you are looking for. So, when you look at page tables, having looked at a page table entry, we know that a page table is nothing but a collection of these page table entries, and the number of entries that you have in every page table depends on the page number field of your virtual address. So, as I mentioned earlier, suppose if you have a 10-bit field in your page number, I can have 2 power 10 different pages. So, you have that many number of entries. And remember that each process can have one or more page tables. The size of the page table, so depends upon the number of entries and the size of the PTE itself. Say for example, if you have 2 power 10 entries and every page table entry is a 4 byte entry, then I have 2 power 10 into 2 power 2, that is 4. So, you have 2 power 12, that is the size of a page table. And page tables, updating the page table and all that is done by means of the MMU hardware. It is of course managed by the memory manager. So, this concept of virtual memory, unlike your cache memory where everything is handled by the cache controller in hardware, when you look at a virtual memory, it is a concept that is implemented at the hardware level and also the operating system. So, the operating system and the hardware work hand in hand to implement the concept of virtual memory. For example, the page table base register, there is a register which is provided by the hardware called the page table base register. But loading the appropriate address into your page table base register is done by the operating system depending on which process is being taken up for execution. So, when a context switch happens, the OS makes sure that the page table base register gets loaded with the appropriate base address of the page table that you are looking for. The hardware again gives you support by an instruction which will help you load a new value into the page table base register. So, providing this page table base register and providing an instruction to load that, all that is the architecture support, and using those instructions, loading the appropriate value into your the appropriate page table base register is done by the operating system when a page fault occurs. So, there is one page table entry per page in virtual address space, that is 1 PTE per every virtual page number, which I have already mentioned. So, normally when we look at a memory hierarchy, even when we looked at a cache, we had 4 basic questions that needed to be answered. Where can a block be placed in the upper level? and we looked at 3 different possibilities in the case of our cache memories. It can either be a fully associative mapping where you have the total freedom of placing it wherever you want, a set associative mapping where you identify a particular set and within the set place it wherever you want, and the third one of course is the most stringent of mapping policies, direct mapping, where you can only place a particular block in a particular location in cache, that is direct mapping. So, which one of these are you going to follow when you are looking at main memory? The second question is, how is a block found if it is available in main memory or not? Are you looking at a tag information per every block? What sort of information do you use? The third one is with respect to your replacement policies. What happens when you are looking for a page and the page is not available in main memory? Then obviously you will have to bring it from secondary storage. So, when you are bringing it from secondary storage, what sort of replacement policies do you use? Are you using a random replacement policy? You are looking at an LRU, looking at FIFO. What is the replacement policy that you look at? And the fourth question of course, your read-write policies. So, what happens on a write? So, when you modified a page and that page has to be, a copy of it is anyway available in your secondary storage. So, when a modification happens, do you do a write through, which means you also update the secondary storage location simultaneously, or do you just maintain a dirty bit and follow the write back policy? So, these are the various questions that you will have to address when you are looking at any memory hierarchy. So, we will see what can be done. So, the main issues, having discussed the basic concept of virtual memory, so the main issues that you will have to look at here is, you will have to choose your page size or block size. Here we are talking about page size here. Page size will have to be chosen in such a way that you are able to minimize the page faults. So, for example, when you are looking at smaller sized pages, what will happen is, if the page size is very small, you can say that you will be able to accommodate more number of pages here, which means more number of processes pages can be accommodated. But at the same time, you are not exploiting too much of spatial locality of reference. The transfer time taken to transfer a large page may be less compared to, depending upon how much of parallelism is available there, it may take less or more time to transfer. So, you will have to look at many of these issues and decide on the page size. The second one, when you look at the 4 questions that we need to have answered, the first one is block placement. Where do you place a page? Normally, it is a fully associative mapping when you look at the transfer of pages between your secondary storage and main storage. Unlike your cache memory where you had all 3 mapping policies which could be followed, when you look at the transfer between your secondary storage and main storage, it is always fully associative mapping. You can fit in a page wherever there is space available. And as far as the identification is concerned, of course, identification we have already indicated how the identification is done. You have a virtual address, the virtual address will have to be translated to a physical address using a page table. So, the page table will give you the virtual to physical address translation and it will give you the page frame address. So, that is how the identification is done, and the replacement policy is typically an LRU replacement policy. It is always a least recently used replacement policy. Remember, we also had a reference bit in the page table entry which will be basically used to find out how frequently the page has been referenced, so that it can be used for designing on the page to be replaced in your LRU. A write policy, of course, it can never be anything else, it can only be a write back policy. So, unlike cache memories where when you are comparing your cache and your main memory, the main memory update may not take too much to write, but here you are looking at main memory and the secondary storage. So, you can't really afford to do a secondary storage write every time, it is totally ruled out. So, we only look at a write back policy where the page, if it is modified, the dirty bit or the modified bit is set to 1, and only when this page is replaced, you write it back into main memory. So, the write policy that you use is a write back policy. What are the pros and cons of paging? We know that it is easy to allocate memory. We know that it is easy to swap out pieces of a program because we are looking at fixed pieces of program called pages. So, when you swap out one page, you are able to accommodate the other page. There is no question of external fragmentation here, that is the main memory getting fragmented, because the main memory is only divided into pages of some fixed size. So, you always have one space which may be able to accommodate the incoming page. So, there is no question of external fragmentation, but internal fragmentation is possible. What you mean by internal fragmentation is, suppose if you are looking at a program which is of size 10K and my page size is 4K, then you definitely have to allocate 3 pages for your program. But the third page, though you have allocated a 4K page, only 2K of your pages page is going to be used for your program. The remaining 2K cannot be allocated to anybody else, any other process, so it becomes an internal fragmentation. And when small sized pages are used, table space can become a serious problem, because you are going to have more number of pages, and with more number of pages your entry is going to be, you are going to have too many entries. So, you have a problem with your table space. This is an example for a 32-bit address space, and suppose if you are looking at 1K sized pages, there are 2 power 22 page table entries, and even if you look at for example, if you look at an 8-byte PTE, that translates to about 2 power 25 bytes size for each page table. And you also have a major problem associated with the virtual memory, which is the memory reference overhead. That is, for every memory access that you will have to do, you will have to do the translation from virtual address to physical address. The page table will have to be accessed. So, that is the first memory access that you are going to do. From there you get the page frame address and then actually reference the data. So, for every memory access that you have to do, you will have to do 2 memory references. So, all along we have been talking about the memory being a bottleneck and how to reduce the memory access time. Now, we are saying for every memory reference, every data access, you will have to do 2 memory references, which definitely is a problem. How are we going to handle this problem? So, this because of this translation, the extra memory access that we are going to do is definitely going to cause a problem, and this makes, for example, the cache access very expensive, because this is the innermost loop that you want to go as fast as possible. So, if you are looking at a cache access, and if it has to be translated to physical address and only then if you have to access the cache, that becomes a problem. So, this problem has already been identified and discussed when we discussed the optimization of caches. For example, we said avoid the address translation during indexing. So, when you access a cache, you will have to do the translation and then index the cache and then do the tag comparison. So, your logical to physical address translation has to happen first, only then you will be able to index the cache. So, we came up with a solution there saying that you can look at virtually indexed, physically tagged caches. So, what we try to do here is we bring in the concept of what is called a translation look aside buffer, a TLB, which is just a cache, a small cache, a special cache, which is used to speed up the translation process. So, we have identified a problem that for every data access you will have to do 2 memory accesses. So, now how is that going to be overcome? That is being overcome by bringing in what is called a TLB. So, the TLB stores the most recent translations. So, what is the virtual address and what is the corresponding physical address? So, it stores the most recent translations. So, whenever you have a virtual address that is getting generated, you do not have to go to the page table to reference that. First of all, look at the TLB, and you know that your locality of reference is anyway going to hold good. So, your TLB is going to, most of the times it is going to hit. So, you get the translation straight away from the TLB, you do not have to access the page tables. So, the translation look aside buffers data structure is basically this. It gives you the virtual address, the corresponding physical address. You have a dirty bit indicating whether it was modified or not. You have a reference bit indicating the access patterns of the page that you are talking about, whether it is a valid entry, what is the access rights that are associated with this particular page. And TLB access time is very fast, normally comparable to the cache access time. So, just like any other cache, the TLB can be organized as fully associative, set associative or direct map, but TLBs are usually small, typically not more than 128 to 256 entries, even on high-end machines, and this permits fully associative lookup on these machines. Most mid-range machines use small n-way set associative organizations also. So, what happens in the case of our cache is, you have the virtual address, you do a TLB lookup to get the translation, and only when the translation is done you are able to access the cache. So, this is the problem that we pointed out earlier, and these are the access times that have been indicated. So, in order to avoid that, what we try to do is machines with TLB go one step further to reduce the number of cycles per cache access. So, they do it by means of overlapping the cache access with the TLB access. So, what we do is high order bits of the virtual address are used to look up at the TLB, while the low order bits are used as indexing into the cache. So, we are trying to overlap the translation that happens and we are with the indexing that is happening. So, that is why we say it is a virtually indexed cache. By the time this translation finishes, you get the physical address and then you tag it physically. So, this is the process that happens. So, it is a virtually indexed but physically tagged cache. So, this is how you overlap your cache access and the TLB access. The same optimization we have discussed with respect to our caches also. We said avoiding address translation during indexing of the caches. It is the same concept that has been highlighted here. So, problems with your overlapped TLB access, overlapped access only works as long as the address bits used to index into the cache do not change as the result of the translation that you are going to do. So, this usually limits things to small caches, large page sizes or high n-way set associative caches if at all you want a large cache. Suppose for example, suppose everything is in the same cache, except that the cache is everything is the same except that the cache is increased to 8K bytes instead of 4K, then that has been indicated here how your associativity can be improved. So, when you go to 8K byte page sizes, either go to two-way set associative cache or you make sure that the software gives you this guarantee of equating the virtual address to your physical address there. So, now how do you differentiate between caches and virtual memory? So, the quantitative differences are in the block sizes or the page sizes. Your pages are much bigger than the blocks that you are talking about in caches. Hit times, your caches obviously have less hit times, and you have a page fault penalty associated with your pages with your virtual memory. The page fault rate is normally slightly higher. The size is also a matter. The page size is an important design decision that you have to do. Replacement, as far as replacement is concerned, as I already mentioned, in the case of cache memories, it is entirely dependent on hardware, whereas when you are looking at virtual memory, it is a combination of the operating system and the hardware that you are looking at. And the size of the virtual address is of course a function of the address size. Though we say it is an illusion of infinite storage, you can't have infinite storage there, you are only restricting it to the size of your virtual address. And you know that disks are also used for file sizes. So, page size, as I already mentioned, larger size indicates smaller page tables, faster cache hit times and efficient page transfer and less TLB misses, whereas small size flexibility, it is a flexibility but it is a high cost, and obviously there is less internal fragmentation when you are looking at smaller sizes. And the process startup time is also going to be reduced when you are looking at smaller page sizes because it can be transferred at a faster rate. And you have a question of hard faults and soft page faults. Hard page faults are those page faults that require issuing a read from secondary storage. Soft page faults are those page faults where the page is already available in main memory. However, the TLB or the page table entry has marked the page as invalid. So, you can also try to look at pages being shared by other processes, and because of this problem happening. Soft faults can also be used to implement certain page replacement algorithms. Now, what happens on a TLB miss? Once a TLB miss is identified, you will only have to traverse the page tables. You do not have an option. So, you will have to traverse the page table, get the translation, and you will have to do it. So, this can be done either using a hardware traversal process or like in the case of your MIPS architecture, you can do a software traversal process. So, most chipsets provide hardware traversal. So, most of the modern operating systems tend to have more TLB faults since they use translation for many things. And examples are shared segments, user level portions of an operating system. And as far as the access time is concerned, so this is an example to tell you how much of penalty that you have to pay. For the given example where your average memory access time is given as 200 nanoseconds, the page fault service time is 8 milliseconds, the probability of miss is p and the probability of hit is 1 minus p. You can calculate the average access time as 200 nanoseconds plus the probability into 8. So this gives you the access times. So even if one access out of 1000 causes a page fault, then the access time is 8.2 microseconds, and that translates to a slowdown by a factor of about 40. So you can imagine how much of miss penalty you have to pay, because a miss penalty here means that you will have to bring it from secondary storage to main storage. So if you want to reduce it by 10%, then you can see how much of modification you will have to do. Now, what factors lead to misses? As before, it can be because of compulsory misses, because the pages have never been seen before. It can be because of capacity misses, because there is not enough misses, and of course conflict misses because of your replacement policy. But technically conflict misses do not exist in a virtual memory because you are looking at a fully associative cache. And the last of all, you also have one more miss, which is called the policy miss, caused when pages were in memory but kicked out prematurely because of the replacement policy. So you will have to look at better replacement policies to avoid this. So to summarize, we have looked at the concept of virtual memory, and this is a concept used to provide an illusion of infinite storage, though it is not actually infinite storage, which removes the restriction that the program size has to be limited to the size of your main memory. You do not have to have your entire program sitting in main memory for execution purposes. Only portions that are on demand will have to be brought in. And paging uses fixed size pages, which is what we have discussed in this module. So when you have a virtual address, that virtual address will have to be translated to a physical address using your memory management unit, and this brings in a drawback of 2 memory accesses. So in order to avoid the drawback, we will have to look at a TLB, which is used to store the most recent translations, and this is a concept which is implemented both as by hardware as well as software. These are the references. Thank you.